All right, so here are some examples. Example, solve the following ODE. ODE means ordinary differential equation. Ordinary means it's easy stuff, not hard. The harder ones will be PDE, partial differential equations, where you deal with partial differentiation. Okay, so that's what that ODE means. Now, first question, A, say y double prime minus 4y prime plus 4y. And B, here's another one, y double prime minus, let's try the same, 4y prime plus this time 13y equal to 0.
Is that one not equal to 0?
Oh. Is this a differential equation?
Yes.
No, it doesn't have an equal sign, so it's not a differential equation. Only when you say equal to something, it's a differential equation. So I said equal to 0. Okay, so let's put our theory at work now. We first have to write down the characteristic equation for this first one. What's the characteristic equation? What do you get? For y double prime, you're going to end up with r squared
minus 4r
plus 4 equals to 0. Okay? And I can factor this. I can factor it as r minus 2 times r minus 2 equal to 0. So the solutions are r equals to 2 and r equals to 2. Oh, what kind of case is this?
Case 2.
Case 2 on the list I said, but that's not a fixed case. So let's just say this is the case where you have a root of multiplicity 2. Okay? In that case, we say one solution is e2 of 2x. That's good. But then we run out of any more function to put on the next for this next one because I already used up this 2, and 2 is all we have, right? So how do you create the other one? You take the first one and multiply by x. So multiply by x. That's it. Only what? 4 lines for this differential equation. Okay. Yeah. How did we achieve this? With lots of theory behind us and just making guesses, and it makes everything easy. Okay. Now let's try the second one. What's the characteristic equation for here? R squared minus 4r plus 13 equals to 0. That's the differential equation. And then I should solve this. Well, there are 2 ways to solve this. First, it can't be factored. You can try to factor this, and it's not going to be factorable. So you have to either use the quadratic formula or use completing the square, which I know a lot of you don't like, but let me tell you, it's a lot easier to do completing the square for this one than using the quadratic formula. So let's try that. What is the completing the square? You first write down inside here the half of this number. So whatever r's coefficient is, divide that into 2 and put it here. What's half of negative 4?
Negative 2.
Negative 2. You just put negative 2 here, and you put r minus 2 squared. And then you have to put something here. And that something has the following property. This plus negative 2 squared. If you expand this, it's going to create negative 2 squared, right? What's negative 2 squared? 4. 4 plus this should equals to 13. What am I? 9. Okay, done. That's completing the square. Easy enough, right? So you do this. Put the 9 to the other side. And then you can take the square root, so you get r minus 2 equals to plus or minus square root of negative 9. What is square root of negative 9? 9 is 3. Square root of 9 is 3. And negative 1 square root is I. So you have plus or minus 3i. R minus 2 will be plus minus 3i. And therefore r will be 2 plus or minus 3i. Okay. In this case, what are the solutions? Y will be C1. The real part we can happily put it over e to the x, right? But for the imaginary part, because of the Euler identity, it creates what kind of functions? sines and cosines. That's what happens, right? So 3 will create both cosine 3x and C2 e to the 2x sine 3x. And if you're anxious to know whether you got this right or wrong, you can actually try to plug this back into this equation, and you'll see that it does satisfy the original equation. They separately do, and they're also linearly independent if you compute the Wronskian, and that's enough. That means this is the general solution. Done.